we are coming to the absolute core of the matrix calculus in general, the dual and adjoint mappings, in particular the joint ones. So this is something which comes up in quantum computing, and as you know, in machine learning, the methods are more and more involving some sorts from, say, statistical physics, quantum computing, etc. So sooner or later it will become part of everybody's daily life, and it's of course already now. So just to come to the point, so if you have a mapping, so say a linear mapping phi from V to W, so you remember that we were thinking about linear forms, say alpha to scalars. So, and this was in the dual space, right? So the space of all linear mappings from a vector space to scalars were called linear forms. The linear forms, typical example, are, for example, the individual coordinates. This is something which is linear and associates to each vector the j's coordinates, right? A linear form. And the dual space is always for finite dimensional spaces only. Take care. For finite dimensional cases, it's isomorphic to the original one. So it's like R to N is the same as R to N star. And in particular, having a scalar product, we simply identify the spaces V with the V, the W with the W star in such a way that we simply leave the first slot free and write a V here, right? So you see, so if this is something like alpha V, right, then it's a linear form associated to a vector V. And you can see immediately that this is just from the formula we had here, right? So you see, so we fix this y, so this part is fixed, so it's a linear form which eats x and provides a scalar. So that's exactly how we saw it all the time, and from the formula you see that it's really giving you all the linear forms, etc. So this is where we are, and now look at the level of the dual of the genuine vector spaces without knowing this identification, in case we have got the scalar product. So we always can look at this, and if the phi goes this way, then of course there will be going the phi star, which gives us the phi star of alpha, and goes also to k, and it's very easy to know how to evaluate it, right? So we simply, if you want to start with something, which is in V, so it's just say a vector u which sits in V, and I now have to evaluate the u on phi star of alpha, and that's simply evaluating alpha on phi u, right? And now you see I didn't have much space in this bottom line here, unfortunately, but I used the formula already identifying this with the scale via the scalar product, but you can use the same brackets as evaluation of the linear forms. So the second term in the bracket will be a linear form, the first term will be, the first slot will be the vector, and that's exactly what the physicists are using. So they call this approach the bracket approach, and they would just deal with this guy, and that will be called bre, and this guy will be called cat, and all together, so I can complete it, and all together you have then the bracket, right? So with this convention, so you see that that each linear mapping phi produces the linear mapping phi star, which goes in the opposite direction from W star to V star, and it's well defined, and that's exactly what we've got here, right? So that's the dual mappings. And as I already revealed, the dual mappings are given in coordinates this way, and if we have got the scalar product on top of that, then we talk about the adjoint mappings, which is the same thing but identified. And you can also forget about the dual spaces then and write it explicitly this way. So the psi star is uniquely defined by this formula, right? And now the bra and cat is not bracket, but it's just the scalar product. So that's the definition of the adjoint mapping. And this looks like strange, but we shall see that it's absolutely amazing and crucial in many areas, and therefore we have to deal with it. And as I already told, this is the bracket form of writing it down in coordinates, and you immediately see that a linear map is adjoint, self-adjoint. Well, no, wrong. If I start with a linear map phi and I look for phi star in terms of a chosen orthonormal basis, then the phi star, the adjoint map, will have the matrix A star, which is the notation for applying both the conjugation and transpose, right? So that comes automatically from here. So here you write down the explicit formula for that with an unknown matrix B, and you immediately find out that the unknown matrix B will be just the A bar transposed, which is the same computation as we did when we computed in the previous presentation, that the condition for the orthogonality of the matrix or unitarity of the matrix of the mapping is that the matrix has to be so this kind of matrix, so this A star has to be the inverse to A, and here it will be just the mapping from for the adjoint. So summarizing this, a mapping is unitary, or a matrix is unitary if and only if the A star is the A inverse, right? And we say that the mapping is self-adjoint if the A star is A, and then it's equivalent to the claim that the adjoint mapping is just the same mapping psi, right? Of course, here I was talking about general mapping phi from V to W. Now when we are talking about the self-adjointness, etc., then we have to restrict ourselves to automorphisms, right? So we are already talking about linear mappings from V to V. So in the complex domain, so the matrix which satisfy A equals A star are called Hermitian matrices. So Hermitian symmetric matrices is another name for the same thing. So in case it would be a real orthogonal space, so the Euclidean space, then the Hermitian matrices are the same thing as the symmetric matrices, right? Because remember, A star is A bar transposed. The conjugation does nothing, so it means A equals A transposed. Right, now I call it remark and an observation, but it's of absolutely crucial interest, right? Because imagine that we have got a Hermitian matrix A. So it's a self-adjoint mapping, which is represented by a Hermitian matrix in any orthonormal frame. And look what happens if we multiply the matrix with the imaginary unit. Right, then writing B star is just doing the same as we did always with the star, and therefore it will be minus B, right? Because the I conjugated is minus I. And such matrices are called anti-Hermitian or Hermitian skew symmetric. And again, well, it doesn't have analogy in the real world, right? So you can't multiply a real matrix with I if you want to stay real. But now, exactly as every real matrix can be decomposed in this way, you simply make A plus A transposed plus A minus A transposed, right? So this will be 2A together, right? Because the A transpose are cancelling each other. And so we add the 1/2 there, and now we have got A equals the sum of the first matrix and the second matrix. And this corresponds to the decomposition of each real matrix into symmetric part and antisymmetric part of it. But in the complex domain, we have analogously the same decomposition where you write A star with instead of A transpose. So this guy will be clearly Hermitian symmetric, right? Because A star star is again A. That's always true, right? So if I hit this guy with a star, it will be A star plus A star star, and it's the same as A plus A star. And here again the same, right? So it will be the same thing up to a sign, because it will be A star minus A. So you see that in particular each matrix A can be expressed as so the whole thing together here as then a matrix C, and the whole matrix, the entire original matrix A, is written explicitly as B plus I times C, and both B and C is now Hermitian, right? Because you easily can see that if you hit with star the whole thing here, because of the 1/2I here downstairs, it will become Hermitian, right? Because this minus psi from here cancels the minus psi from here. So you simply have got two Hermitian matrices, B and C, and this is just a complete analog to the decomposition of complex numbers into its real and purely imaginary components. So you often also find in the literature writing B as the real part of A and C as the imaginary part of A. Right, so that's a nice observation. We shall come back soon to again, at least in the next. So just to keep it in front of our eyes, let's write explicitly, again wrong, A equals simply B plus I times C. This is a generic, any linear mapping in coordinates, a matrix. This is a self-adjoint one. This is also a self-adjoint one. And exactly this observation is the absolutely crucial part of why the self-adjoint things are so much used in say physics, and they play the role of our observations in quantum mechanics and the same in quantum computing, and I guess the quantum computers will start existing soon in real use, and then this will become an absolutely essential part of the elementary linear algebra soon. So let's now come back to the self-adjoint ones, because the self-adjoint ones are so useful in front of from the point of view of the physics and the observations, because the self-adjoint operators have got that absolutely striking property in view of how it decomposes into, well, how the space is decomposed into invariant subspaces of the kind of spanned by eigenvectors, and the eigenvalues, as we shall see, are always real numbers, and therefore the eigenvalues are the things we observe, because that's how we understand, say, quantum mechanics, etc., instead of working with positions as a real numbers somewhere. We measure something, and the measured things are the eigenvalues, the things which propagate themselves because they are coming back to itself, right, when iterating. And this is a simple observation, right? So you start with psi, a linear map with a matrix A in some orthonormal basis, and now we immediately see that whenever you have an invariant subspace, then the self-adjoint things, due to this property, keep the orthogonal complement again invariant. That's crucial, because then, of course, again, as before, we can repeat the argumentation with the orthogonal mappings or the unitary mappings, and showing that actually there always will be a orthonormal base where the matrix is diagonal, and on the diagonal you have the eigenvalues. So the geometric multiplicity of the individual eigenvalues must always be the same as the algebraic one. And moreover, if you just observe what could happen with the eigenvalues, then you see that if you just write AXX in scalar product, then it will be lambda times XX. But because it's self-adjoint, you can throw the A to the other side, but then you get a lambda X here. But from the second position, the scalars are pulled out with a bar. So they are conjugated, and therefore you see, because XX is a non-zero real scalar, you see that lambda bar is lambda, which is nothing but the fact that they must be real, right? So you see, all the eigenvalues of Hermitian matrices are always real, the same thing as all the eigenvalues of the self-adjoint mappings are real. So you see, the orthogonal complements of invariant subspaces of self-adjoint mappings are invariant again, and all the eigenvalues are always real. So the diagonal version of our self-adjoint mapping will always have eigenvalues on the diagonal. In the real world, this concerns the symmetric matrices. So if you have some linear map with a symmetric matrix, then of course everything applies, and you will necessarily get all the eigenvalues. You necessarily get an orthonormal basis in which it's diagonal, and all the eigenvalues will be real. Right. This is very nice. And so we come to the final conclusion, which is now at a level of observation only. So the only thing we have to take care of is now to remind you the concept of the projection, right? A projection means a linear map which is idempotent. We talked about that already. So P square is the same as P. So this means that the restriction of P to its image is identity, and actually choosing the image and the kernel is automatically prescribing the projection uniquely, right? And if we want the projection to be orthogonal, then means that the kernel should be orthogonal to the image, and then already choosing the image gives you the projection uniquely. And this is then the rephrasing only of what we have already deduced. If we have got that's the very famous and very crucial spectral decomposition theorem. So it says that if you have a self-adjoint mapping of on a unitary space or on a real vector space with scalar product, then if you take the distinct eigenvalues, so the spectrum of the mapping, so we don't care about the multiplicity, and we know already that in the self-adjoint case, the dimension of the space of eigenvectors to each of those values will be the same as the multiplicity of the eigenvalue as a root of the characteristic polynomial. And all the eigenspaces will be mutually orthogonal. And if we consider the k orthogonal projections, then there are the k real eigenvalues, and the whole mapping psi is given as the sum of the orthogonal projections to the eigenspaces multiplied by the eigenvalues. And that's it. So a crucial theorem. Please think carefully about what it says. Look it after. You can find dozens of nice presentations with pictures and whatever if you were not happy enough with my short description.